Hi students, welcome to today's class. Today's topic is implications of Shannon-Hartley law. Okay, here we have two implications to Shannon-Hartley law, that is Shannon limit and bandwidth SNR trade-off. That is, by using Shannon-Hartley law, we have the equation for channel capacity C is equal to B log 1 plus S by N. And also we have a noise equation for noise is eta B. B means bandwidth. From the above equation, if we increase the value of bandwidth, the channel capacity should also increase. But since the noise power N equal to eta B, as we increase the bandwidth B, SNR will be decreases. Thus, the product beta deal with the 1 plus S by N. Okay, then it will increase at only up to a certain value and then it will remains as a constant. Okay, so this is the case of this equation. That is, in order to transmit a lot of data, we want to increase the capacity of a channel. So by using this equation, if we increases the capacity of a channel, if we want to increase the capacity of channel, we should increase the bandwidth of the channel. Okay, so a problem will exist if we increase the bandwidth of the channel, the noise will be increased. So the system will have a high noise, and also if noise is increased, the signal to noise ratio will be decreased. So this bandwidth is related to this 1 plus, that is log 1 by 1 plus SNR. So this bandwidth and SNR should be maintained in a proper manner in order to get a high capacity. So this is discussed in this Shannon limit. There is a limit of bandwidth to increase in order to get a higher capacity. So we want to deal with we want to limit these two in a good manner. So in order to increase the capacity, we want to increase the bandwidth, but in certain limit, it should be remain a constant. Okay, so we have C is equal to B log 1 plus S by N. So we can substitute N equal to eta B. So we get B log 1 plus S by eta B. Okay, then multiply and divided with the S eta. Okay, then capacity C is equal to S eta multiplied, and we at the same time we are dividing S eta with the equation B log 1 plus S by eta B. Okay, now we are taking S by eta into one side and we are taking B eta by S to the other side. So I take S by eta to one side and the remaining portion B eta by S to other portion log 1 plus S by eta B. Okay, now this is, we have x log x. So we can uh, write this term to the power of this term. Okay, that is S by eta log 1 plus S by eta raised to beta B eta by S. Okay, so x log x means log x raised to x. Okay, so we take this term to the power of this 1 plus S eta B. Okay, by looking these two, it is clear that S by eta B power beta B by S. That is, this power is the reciprocal of this term. Okay, now substitute this S by eta B, that is the denominator 1 plus S by eta B. This S by eta B to x. So we get C is equal to S by eta log 1 plus x raised to 1 by x, because the power is reciprocal of this S by eta B, that is reciprocal of beta B eta by S. Okay, so we are providing, we get like this, C is equal to S by eta log 1 plus x raised to 1 by x. Okay, now applying the limit B to infinity. So when we are giving a maximum bandwidth, what will happen? Then x is equal to, at x is equal to 0. So the C is equal to limit B equal to infinity or x tends to 0, S by eta log 1 plus x raised to 1 by x. So we have in equation limit x tends to 0 at the at this time, that is at beta tends to infinity, x equal to 0. Okay, now we have an equation, limit x tends to 0, log 1 plus x raised to 1 by x is equal to log e to base 2. Okay, log e. Okay, now substitute this term as log e. Then we get c infinity is equal to s by eta. For this value log 1 plus x raised to 1 by x, we are replace it with the log e to the base 2. Now we get an infinity. If we increase the capacity to an infinite value, if we increase the bandwidth to an infinite value, we get a maximum capacity c is equal to s by eta into 1.4426 bits per second. This is the maximum capacity we will get when we are increasing bandwidth to infinity. Okay, so for an ideal communication system, we prefer data bit rate, that is R equal to C. Okay, for ideal system, rate of transmission R is equal to capacity. So if we represent transmitted signal S, so we can represent S as EBC. Okay, EBC, EB into C. This capacity. Then we have C is equal to B log 1 plus, in order to S by N, we can substitute S as EBC and N as eta B. Then we get C by B is equal to log 1 plus EBC by eta B. Okay, the ratio C by B is called a bandwidth efficiency. This term is called a bandwidth efficiency. Now for an ideal system R equal to C, now we can substitute instead of C, we can substitute R. Then we get R by B is equal to log 1 plus EBC by eta B. Okay. Now taking the antilog of this equation, we get 2 raised to R by B is equal to this term. Okay, we are taking antilog. That is 2 raised to R by B or C by B is equal to 1 plus eta B by 1 by EBC by eta B. Okay, 1 plus EBC by eta B. Now 2 raised to C by B, take this one here, then we get 2 raised to C by B minus 1 is equal to EBC by eta B. Now we are deriving equation for EB by eta. Okay, now EB by eta is equal to 2 raised to C by B minus 1 by C by B. Okay, here R equal to C, then we can change C as R. Okay, replace C with R. Then EB by eta equal to 2 raised to R by B minus 1 by R by B. So then a graph is plotted with EB by eta. So when a graph is plotted with this EB by eta and this R by B. Okay, EB by eta and R by B. EB by eta on x-axis and R by B on y-axis, we get this graph. This graph is called bandwidth efficiency diagram. So R by B or C by B is bandwidth efficiency. So this graph is called a bandwidth efficiency diagram. So look at this graph. Here x-axis is EB by eta and y-axis is R by B. Okay, then we get a curve like this. So here this boundary curve is called R equal to C. This is the capacity area. Okay, the capacity diagram. We can say this diagram as capacity diagram. The region here is R greater than C, and region here down the region is called R less than C. So for an error-free transmission, R should be less than C or R equal to C. That is the region under this graph. Okay, and we cannot get an error-free transmission. That is no error-free transmission at R greater than C. Okay, now when we are plotting a line here in this convergence point, that is this is the point when this R by B, that is bandwidth efficiency, is maximum. R by B is infinity. This is going to infinity, and EB by eta value is, this crossing point value is minus 1.6. Okay, this is 0 value, this is minus 1.6. This point, that is minus 1.6 point, is called Shannon's limit. That is, what is Shannon's limit? When r by b is infinity, it is going to infinity, right? So this is going downwards, this is going to infinity. At that time, the value of EB by eta is equal to minus 1.6. This is the Shannon limit. This is called Shannon limit, that is minus 1.6 TB, that is EB by eta. Okay, EB by eta, that is minus 1.6 TB. And the corresponding channel capacity. So the corresponding channel capacity at maximum bandwidth, the channel capacity is equal to S by eta into 1.4426 bits per second. This is the bandwidth efficiency diagram. Okay, so this is about Shannon. This is about Shannon limit. Okay, now we can go through conclusion based on this Shannon limit. So we discussed what is Shannon limit, and in order to get higher capacity, we want to increase the bandwidth. So at infinite bandwidth, we get a maximum capacity of this value, that is S by eta into 1.4426, and this is the Shannon limit point. At Shannon limit point, the R by B value will be going to infinity, and EB by eta value will be minus 1.6. So we can have some conclusion based on this Shannon limit. The first conclusion is, for a infinite bandwidth, C infinity is equal to S by eta into 1.4426 is the infinite bandwidth. Okay, for an infinite bandwidth, the capacity C is equal to S by eta 1.4426. Okay, now we can write this as this S can be replaced by EB into R, that is EBC. EBC. So instead of EB, we already said S is replaced with the EBC. So we are replacing C with the R. So EB R by eta. So R means here the capacity is infinity. So replace R with the C infinity. Then we get 1.4426 EB C infinity by eta. So by cancelling these two infinity, we get EB by eta is equal to 1 by 1.4426, that is 0.694. Okay, so EB by eta at dB value, at dB, in order to convert dB, we want to take 10 log that value. So EB by eta is 1 by 1.4426. So in dB, we can write 10 log this 1 by 1.4426, that is equal to minus 1.588 dB, that is equal to, by rounding, we get minus 1.6 dB. So this is the value of EB by eta when the bandwidth is infinite. We have a capacity of maximum value, that is EB by eta is equal to minus 1.6 dB for bandwidth, infinite bandwidth. This value EB by eta is called Shannon limit, and the capacity at Shannon limit C infinity is equal to S by eta into 1.4426. So this is the first conclusion we are reaching in the Shannon limit. That is, first point is, at infinite bandwidth, we have a capacity, maximum capacity of 1.4426 into S by eta, and also at infinite bandwidth, we have a Shannon limit, EB by eta is equal to, in dB, minus 1.6 dB. This is the first conclusion. Then second conclusion is, the bandwidth efficiency diagram is separated into two regions. That is, this is the bandwidth efficiency diagram. This can be separated into two regions. That is, R less than C. In R less than C, we have a error-free transmission is possible. For R greater than C, error-free transmission is not possible, and the curve R equal to C is called a capacity boundary. So this curve is called a capacity boundary, and below this curve, we get an error-free transmission, and above this curve, we did not get any error-free transmission. Okay, so that's all about Shannon limit. Then second implication is bandwidth SNR trade-off. That is, there should be a trade-off between bandwidth and SNR. That means we, in order to increase the capacity, we don't want to increase bandwidth too much, and if we increases bandwidth too much, the SNR will decrease. And if we decreases the noise and increases the SNR, bandwidth will be reduced. So we want to maintain a value, a maximum value between bandwidth and SNR. So bandwidth and SNR always should be maintained in a proper manner in order to increase the capacity. Suppose this can be viewed by an example, that is C is equal to, we have bandwidth equal to 4 kilohertz and SNR we are taking as 7. Now we have capacity C is equal to B1 log 1 plus SNR. Now we have capacity is equal to bandwidth is 4 into 10 raised to 3, that is 4 kilohertz, log 1 plus SNR is 7. So 1 plus 7, we get 4 into 10 raised to 3 log 8, that is 2 raised to 3. Then we get 3 into 4, that is 12 10 raised to 3 bits per second. So we get a capacity 12K capacity for a bandwidth 4K. Now and SNR 7. Now keeping the same channel capacity, SNR is increased to 15. So our SNR is increased. Okay. So SNR increased. Then what will happen to bandwidth? So see, the same capacity is maintained, that is 12K, 12 10 raised to 3 into B2 log 1 plus SNR is increased to 15. 1 plus 15, that is 16, that is 2 raised to 4. From this we get B2 as 3 kilohertz. So when we increases the SNR, bandwidth is reduced. Okay, that is bandwidth is reduced from 4 to 3 for the same capacity. So if we want to increase the capacity, the SNR will decrease. Sorry, if we increase the bandwidth in order to increase the capacity, the SNR will decrease. If we increase the signal to noise ratio, the bandwidth will decrease. So we should maintain a proper ratio between this bandwidth and SNR. Okay, so we have noise power related to noise is bandwidth is N equal to eta B, which bandwidth decreases from 4 kilohertz to 3 kilohertz. When bandwidth decreases from 4 to 3 kilohertz, noise also indicating a SNR. Okay, now we have N1 is equal to N beta 1, sorry, NB1, that is, sorry, N1 is equal to eta B1, eta into 4 kilohertz. In second case, N2 is equal to eta B2, that is eta into 3 kilohertz. Okay, the bandwidth is reduced to 3. Then next we have SNR2 by SNR1. So we are taking the signal to noise ratio of second situation by first situation. That is S2N2 by S1N1. That is S2S1 into N1 by N2. That is equal to 2.14. So from this we get S2 by S1 is equal to N1, in case of N1 we are writing NB1 by NB2 equal to 2.14. Okay. Now we get 2.14 from SNR2 is SNR is 15, SNR1 is 7. So 15 by 7 we get 2.14. Okay. Now we are substituting this equation S2 by S1 into N1 by N2 is equal to 2.14. Then we have N1 is equal to eta B1 and eta B2. Now eta B1, that first bandwidth is 4, second bandwidth is 3. So S2 by S1 into 4 by 3 is equal to 2.14. Then we get S2 by S1 as 1.605. That is, signal power is reduced to 1.605 if we increase the bandwidth. So here a 25% of reduced in bandwidth, that is bandwidth is reduced from 4 to 3, we require a 60% increase in signal power for maintaining the same channel capacity. So in order to maintain the same channel capacity, here the bandwidth is reduced from 4 to 3. So since the bandwidth is reduced, we want to increase the SNR with a 60% increase. Okay, so there should be a deal or a trade-off between SNR and bandwidth. So in order to increase the capacity, we have no provision to increase the bandwidth in too much way, because if we increase bandwidth in a great way, the SNR will be reduced. If we increase the SNR, the bandwidth will reduce. So we want to keep both in a trade-off between both value. So this is SNR and this is bandwidth. This is the bandwidth SNR trade-off curve. Okay, and we have C is equal to B log 1 plus S by N. Then C by B is equal to log N 1 plus S by N. Then we are taking reciprocal, B by C is equal to 1 by log 1 plus S by N. So this way we are creating a curve. So we want to adjust, or we want to make a trade-off between bandwidth and SNR in order to increase the capacity. So this bandwidth SNR trade-off, there are also some conclusion or inferences. That is, two inferences are the first one. For a noiseless channel, we have infinite capacity. That is, when this noise is equal to 0, we have now S by N is infinity. That is, C is equal to B log 1 plus infinity. So we get the capacity of channel is infinity. So a noiseless channel, or a channel with no noise, the capacity will be infinity. Okay. So infinite bandwidth channel has a limited capacity. If we are providing an infinite bandwidth, we have a limited capacity, that is C is equal to 1.4426 S by eta. This is Shannon limit. If bandwidth approaches to infinity, capacity does not approaches to infinity, but capacity will take a upper limit, that is a maximum value capacity. So when we increases the bandwidth to an infinite value, the capacity will not limit to infinite capacity. The capacity will be maximum. The capacity will be infinity only when the noise will become 0. Okay. These are the implications of Shannon-Hartley theorem. So that's all about today's class. Thank you.